recording. So section 6.5, I want to just show you a few more examples here. These we'll look at in the book. So example 2 says find the least squares solution for this system, where there's the matrix A and there's the vector B. What can you tell me, looking at this example 2? Okay, what can you tell me about the column vectors of this matrix A? What can you tell me about the column vectors of this? Hold on. Wait, where did it go? Am I missing it? Is it? Okay, good. The column vectors of the matrix A. That's right, Mikhail. They are linearly independent. The first vector equals the sum of the first vector with all the ones in it equals what? It would equal the sum of the column vectors 2, 3, and 4, right? So in other words, the first vector equals 1 times the second column vector plus 1 times the third column vector plus 1 times the fourth column vector. So the fact that the first column vector of the matrix A is a linear combination of the other 3 column vectors of the matrix A, the column vectors of the matrix A are linearly dependent, and so the matrix A is not invertible. So the formula that maybe I can just show you here. If we go a little bit down here in theorem 14, this formula here in theorem 14 we used in the previous example, but it's because the x hat formula there, it's because conditions A, B, and C were met. And in fact, the fact that the columns of the matrix A were linearly independent means that A transpose A was invertible. But you don't always have that situation like you see here in theorem 14. Sometimes you have a situation like you see here in example 2, where the matrix A, the columns are linearly dependent. That's okay. That's okay. All we're going to do then is, in the solution, set up the normal equations. We're going to compute A transpose A and A transpose B. Okay. And then once we get that, we'll have the augmented matrix for A transpose A times X equals A transpose B. And we can row reduce that matrix and solve for the least squares solution. Okay, so you can't use that inverse formula, but you can still solve for the least squares solution. And if you look here, in particular here, is at that augmented matrix, is the least squares solution going to be unique? No, it's not going to be unique. You're going to have free variables in there, right? So if you were to solve, go ahead and solve this, the general least squares solution would be x1 equals 3 minus x4. So x4 is free, and then x1 is 3 minus x4. Well, let me go reverse. x3 is negative 2 plus x4, x2 is -5 plus x4, and x1 is 3 minus x4. And so you have a least squares solution where you have a free variable, and so there's an infinite number of least squares solutions. Now that is not generally desirable, right? We don't generally, if we want a least squares solution, it's generally desirable, particularly in applications, to have a one least squares solution. But in this case, you do not, because the column vectors of the matrix A were not linearly independent. So you see, when you collect data and put it in a matrix A, you don't want data to be redundant, because if data is redundant, in other words, if you think of data being column vectors of data, you generally want your column vectors of data to be linearly independent, so that the information is different. If you have two data columns that are linearly dependent, or if you have a data column that's some linear combination of your other data columns, then you have non-essential information essentially in your data matrix. You have information that is like repeated, so to speak, effectively. And so, and this is sort of a lead into what we're going to talk about in section 6.6 on Wednesday, where we're going to talk about some linear models, some applications, some word problems. But okay, I wanted you to see this, and also, I wanted to show you something else here. So example 4 here says, well, they talk about alternatives calculations for least square solutions. So if you have a matrix A where the columns are orthogonal, then you can find the projection vector B using the orthogonal decomposition theorem from section theorem 8, section 6.3. Okay, you can find the projection vector B hat this way. You can find that projection vector B hat this way, and then you can solve A times X hat equals B hat. Okay, so let me just check one thing on this. I want to make sure. Yeah, so this is, I'm going to say this the right way. Sorry, give me just one moment here. So the coefficients of vectors A1, which is 8/4, and vector A2, which is 45/90, that's going to be your least squares solution, because the linear combination of A1 and A2 with those values gives you the projection vector, the projection of the vector B onto the column space of A. So in that case, you have, it's very simple. But of course, many times you don't have a matrix A with orthogonal columns. Now, you can create a subspace if you have a matrix A with columns that are linearly, that are not orthogonal. Well, those columns form a subspace, the column space of the matrix A. You can find an equivalent column space using Gram-Schmidt process, but that takes time. Okay, so I think on that note, I want to stop there. Are there any questions before I stop the recording? We'll talk a little more about 6.5 on Wednesday, but Are there any questions? Okay, very good.